Okay, so yeah, definitely chime in if there's any issues, and certainly if there's any questions. We're just a slightly late start. And I want to pick up where the video left off, which was reactions of alkenes. And the three reactions that I went over that are just to be able to recognize what this reaction does and predict the product, for example, would be the hydrogenation and the bromination and the hydration. Oops. So hydrogenation and hydration sound a lot alike, but this is the addition of hydrogen, addition of a molecule of hydrogen or two atoms of hydrogen across a double bond. Bromination's addition of a molecule of bromine or one bromine each across the double bond. And hydration is like water, right? So addition of water across the double bond. So just to show a few more just examples, because all I did was show some general examples. And so let's say you have a cyclopentene like this. If you want to hydrogenate, add hydrogen, the conditions we're gonna just have always the same. Hydrogen over the catalyst, palladium. So I'll point out a few other features here for a little bit of breadth and depth, help us remember. So this is a metal catalyst. So if you remember a little bit more about each reaction, it helps bring to mind the basics, and you remember, wait, okay, so hydrogenation, that one was the one with the metal. Oh yeah, it was H2PD. The neurons connect in a network, when you learn more facts surrounding an initial, fact. So the outcome of this is best seen if you, want to make sure you're not losing things along the way or having too many things bonded. So each of these carbons of the alkene have a hydrogen on it already. So those, remember, are implied hydrogens. And then if we're adding a hydrogen, again, additionally to each of these carbons, then we say to ourselves, the double bond goes away, and then we add two more hydrogens, so we end up with a fully saturated cyclopentane. And so we added H2 across the double bond, which is no longer there. So note, double bond has reacted. And is no longer there. This is going to be true for all of these. So the most common error I've seen is when you have the products, whether there's hydrogens added or bromine or water, those are added, but then the double bond is still there. And it's like, well, there's a big major point missing there, because it's the double bond that actually causes the reaction to occur and is involved in it. So an example of bromination, going to the next one. So that was hydrogenation. And then the next example, bromination example. let's start with something like this. So 1, 2, 3, 4, 5. It's a pentene. Actually, you would number it from the other direction. 1, 2. It would be a 2N pentene, if you want to name it. And adding bromine, typically in some organic solvent. I don't remember what we put earlier. Often this is in a solvent called dichloromethane, which has an odd name, CH2Cl2. But anyway, this is just some kind of relatively nonpolar solvent. But the bromine is the important part. And 1, 2. So the numbering actually, if you number to yourself, helps keep track. And the bromine, and remember there's, again, I did always do that. Let's see. Okay, there's implied hydrogens there. And remember, alkenes are trans or cis, so this is trans as it's shown. So those hydrogens are still there. And then you have the bromines added, one across there. So a bromine across, 2 bromines added across the double bond, 1 to each bond of the carbons of what was the double bond is no longer a double bond. So I suppose if we wanted to name this, it would be 2,3 dibromo and pentane. Now it's a pentane. It's no longer a pentene. One interesting thing to point out about this reaction, a little bit further detail, if we had it reacting on an alkene in a ring, for example, this alkene is trigonal planar. So going back to our geometry, it's basically this area of the molecule is flat. If we add our bromines, one bromine will add pointing up and the other will add pointing down. So the 2 hydrogens are still there. Well, I should change the bond types. So if one bromine comes in and adds to the top, that means the hydrogen that was there would be pointing down. And then if the other bromine is added, it would come in from the other side. So if you were to delve into the real mechanism of this reaction, this becomes much more apparent. But what you want to remember with this, if it ever comes up, is that the bromines add trans. So it's a trans addition. Okay, so going back, we have our alkene, which is trigonal planar. In the bromine reaction, and I suppose I would have my solvent for completeness, and one of the bromines will first add to one side with equal likelihood, and then the next bromine would have to come in from the other side compared to where the first one came in. And so trans addition is what happens. That didn't really matter up here, notice, because there is no cis-trans when you can have free rotation. Remember, it's rings, substituents on rings, where cis and trans is used. Trans and cis are used in alkenes like this one over here. So cis and trans always have the same basic meaning, cis on the same side, trans on the opposite sides. Notice how we're sort of bringing everything in, different aspects of knowledge from the different things we've talked about all quarter so far. The material just really continues to build. Any questions so far? Okay. So then the third one was hydration. So I'll show an example of that, hydration. With these first three, you really just want to recognize where you're starting and where you're going to end up, and maybe a few other little minor details, but you're not being asked to learn how these reactions actually go. You're not being asked to learn their reaction mechanisms. So hydration. So let me draw another alkene. And let's change it up a little bit. Let's do this. So the hydration conditions was basically acidic water, H2O, H2SO4. And what we're going to find, I think we're going to be revisiting this a little bit later in the quarter, acids in water, aqueous acids. For that matter, we could talk about aqueous bases, but AQUEOUS, aqueous acid. Basically, when you have acid in water or base in, or I'm going to concentrate on acid and water, excuse me. So acid and water, these will react together actually, and the species that's actually reacting is hydronium ion, which looks something like this. So source of hydronium ion. Hydronium ion. And that probably looks familiar from Gen Chem in some reaction balancing stuff you might have done as H3O plus. But that's essentially when you throw H2SO4 in water and use it as an aqueous acid in a reaction, the reaction's really proceeding through the use of hydronium ion. The same would be true if you had sulfuric or hydrochloric acid or phosphoric acid or anything like that mixed with water. It's a little bit of a digression, but I think we're going to see this again in the next chapter, probably. So, but the important thing to remember here is, the gist of it is that you'll get the OH and the H adding across the double bond, and the double bond goes away. So the OH will end up on one carbon and the H will end up on the other carbon. And this looks a little funny because I didn't draw my implied hydrogen in there. So, well, it still looks a little bit funny, but that's okay. So this hydrogen just stayed where it was. And notice it was the addition of water to the double bond across the double, and the double bond is no longer there. Any questions or comments on that? So what I want to move to, and I'm actually going to come back to this, hopefully, if I remember. The fourth reaction type was addition of, did I number these? I don't think I numbered them. Yeah. Addition of HBr or HCl to alkenes. And the overall reaction that I showed, but it didn't show, I don't think I showed an example of yet. So let me make another alkene. This is a 1, 2, 3, 4, 5, 6. This is 1, 2, 3 hexene. If we add HBr to this, the reaction, if we remind ourselves again, if you don't, after a while you won't have to draw in implied hydrogens, but it helps the first several times you practice it. And I've given you a lot of practice problems in the book, by the way. So that's the starting material. the reactant, and this will go to adding a hydrogen to one carbon of the double bond and a bromine to the other carbon of the double bond. 1, 2, 3, 4, 5, 6. And so not to lose track of where we were, so the hydrogens that were there are still there. And we add a hydrogen to one and a bromine to the other. So we've added HBr across what was the double bond. Likewise, if this was a chlorine, you could add HCl across the double bond. So I chose this reaction to go into talking about how the reaction occurs and diving into the mechanism of it, because that's a really huge part of organic synthesis and organic chemistry. And we're not going to do that for every reaction we see. In this case, we're only doing it for one of the four, right? So the top three are mostly recognizing, but the fourth one is a good one to look at the details of it. And this will progress into sort of one more level of thinking beyond that. Where this is headed is that if we understand, say, for example, how this reaction works, we'll be able to spot this same reaction over and over again in similar situations. But more than that, we might be able to predict something that we haven't seen yet based on what we learn here. And so I feel it's important to do stuff like that, because that's really what science is all about. It's not just recognizing things that have already been learned. It's learning details and then using that knowledge to maybe predict something you haven't seen before. And I think that we'll have just enough time. We'll have plenty of time to do that. I think, yeah, okay, so let me go ahead before I go off on another subject. So the way this reaction really proceeds, and I did go into this a little bit in the video. I'm drawing specifically out the carbons of the alkene. Okay, so this should really look, this is 1, 2, 3, 4, 5, 6, 3, 4. I went into the nature of the double bond last time, where pointing out like these two lines are a notation, but one of these bonds is a different type of bond called a pi bond. You could look that up if you're interested. But the key thing is that it has a pair of electrons that are more reactive than the other electrons of the other bond that's present here. And what they're looking to react to, since electrons are negatively charged, are regions of positive charge, or it could be a region of partial positive charge. And that's what you have with a molecule like HBr or HCl up here. We know about electronegativity. The bromine is electronegative. And we can indicate polarity using the Greek letter delta. So delta plus, delta minus, delta plus. So the electronegative bromine pulls electron density toward it and away from the less electronegative hydrogen. That's basically what electronegativity is, right? So, and you have, remember, there's a pair of electrons here being shared in a covalent bond. One of my pet peeves is that they don't really emphasize covalent bonding enough in general chemistry. So, but back to the point, these electrons, which are negatively charged and reactive, can form a new bond to the proton, which is all that's really here. I shouldn't draw it like that. But a hydrogen is just a proton and an electron. So the proton is really represented by the H symbol, and the one electron of hydrogen is right here where I'm pointing. So this is a bond forming reaction here. Actually, so this bond is actually breaking in order to form the new bond. And then since a proton can't form two bonds at the same time, these electrons are both displaced onto the more electronegative bromine. And so the result of those arrows, and this arrow is bond breaking. I gotta save this. Excuse me, because I forgot to save it yet. I'll just save it as untitled for now. And then the result of those arrows, so this bond breaks, forms the new bond, breaks this bond, and the result of all that is this is all still the same. That bond to that carbon is still there. This is all still the same. That hydrogen is still there. But now we have a new bond from carbon to hydrogen. And once these electrons over here go onto the bromine, you end up with a bromine that's negatively charged. Now it has extra electron density, while carbon 3 here has lost electrons. It had 4 bonds, now it only has 3, and a carbon with only 3 bonds and no extra electrons beyond that is a plus charge, or a carbocation. The bromine then, having extra electron density, in fact, this bromine, to be really specific, has 4 lone pairs on it, whereas before it only had 3. Once the 2 electrons that were this covalent bond go on to the bromine, now it's got 4, and now it's negatively charged. And these electrons, it's all set up to go and just simply form the final bond there. Bond forming. And the result of that bond forming is, once again, everything else the same. That hydrogen was added, and now the bromine is here with the final last bond being formed right there. So notice in the end, from start to finish, the alkene plus HBr, it's still very much like the reactions we saw above. Hydrogen adds to one carbon, bromine adds to the other carbon. So just to let you know that I'm not completely off the rails here, you can see, good, this is all in your book, actually, in Mastering Reactions. Page 422, 423. Goes into all this, and actually it continues on to what I'm going to continue on with right now, which is some more detail about where does the bromine go and where does the hydrogen go if both sides of the alkene are not the same. So this is a really interesting thing. The molecule I started with here is really symmetric, actually. If you look at it, it's like that both carbons of the alkene have an ethyl group attached and a hydrogen attached. So that's often not the case, usually not the case. So if you had an alkene like this, I'll draw on this implied hydrogen. Now What's changed is really that this carbon here on the left has no hydrogens on it. I could draw the carbons in a little bit like this for clarity. So notice, no H's. When you add the bromine, HBr, and I'm going to go ahead and do the arrows because they're always the same. It seemed like a lot maybe above, but that's it. They're always going to be the same from now on. Bond forming, bond breaking. Plus new hydrogen on there. Now there's 2 hydrogens on there. There's our carbocation. The bromine minus that got generated forms bond. Continue down here. Oops. Now the bromine's here. And we've added HBr across the double bond's gone. But notice I purposely put the I had the bromine go to this carbon and not this carbon. I had the hydrogen initially, when this bond forms here, the hydrogen initially goes to the carbon on the right. And there's a couple ways, there's 2 ways to remember this. The way that I don't like, but that many people like, and so I'm going to include it, is to remember Markovnikov's rule. So I'm not a big rules guy, because I don't have a good memory for it. Markovnikov's rule. But many people prefer to just memorize the rule rather than the second way to remember it. Markovnikov's rule says basically that hydrogen adds first, it's long too, first to the carbon that has more hydrogens to begin with. Leading to, I'll say, leading to the bromine or chlorine adding to the other carbon, adding to the carbon that has fewer H's. Now you see why I don't like to memorize stuff like this. But what this really is an explanation, it's noticing that it's always consistent. Thus, you can come up with a rule. But there's a reason why it's always consistent. The reason it's always consistent is that a tertiary carbocation like this, a carbocation with no hydrogens on it, is more stable carbocation. And this is in that mastering reactions section I referred to. That's a more stable carbocation than if the carbocation was here. Tertiary carbocation. And we've used the words primary, secondary, tertiary. Tertiary. The carbon's got 3 other carbon groups attached and no hydrogens. So let me just point out down here, note, if this went the other way at the beginning, we would have the hydrogen having added there, the carbocation there, with hydrogen and that. So, and this is a secondary carbocation. secondary carbocation, less stable. So if this reaction went the other way, in other words, from these starting conditions to here, alternative, I'll say the worse worse than this other one. So because this carbocation is more stable, it takes less energy to get to it forming. If it takes less energy to get here, it's going to be preferred. Then the bromine comes in and you get your major product here. While the higher energy carbocation is more difficult, obviously, and so this is a minor product if it even occurs at all. Maybe you get a little bit of this. So this is really cool, actually. If you take the bird's eye view, step back for a second here. Our knowledge of structure and bonding will allow us to predict this reaction. First of all, you've got electrons that are negative, you've got HBr that is polarized, and so the new bond forms, the old bonds break, it leaves the more stable carbocation, which is going to really be the way it goes every time, thus leading to Markovnikov's rule. When the hydrogen adds first to the carbon that already has more hydrogens, that's what's happening in the top scenario, this hydrogen added. And that leaves, but the real reason is because it leaves a tertiary carbocation. One more thing to point out, if it's a choice between a secondary and a primary carbocation, the secondary would be more stable. Maybe I'll make a little note of that. So likewise, if it is a choice between secondary and primary carbocations, if it is would be formed. Okay. Most of the time, you can't even get a primary carbocation. It's so unstable. So I said earlier, so let's just pause and go back. Earlier, we all the way up here, we basically are memorizing and recognizing the first three reaction types: hydrogenation, bromination, hydration. Then we dialed down way down into the details of addition of HBr or HCl. Certainly you could just remember the net reaction. And that's going to be worth some points. You know, what's the product of these things when you mix them together? Then we dialed way down into the details to try to understand what is going on here. And it's all based on these electronic things going on. Literally electronic. Electricity is electrons. So, and now we have this trend and these rules that relate to the stability of carbocations that can form. That leads to where exactly the bromine goes, really, when you think about it. That's going to be what chemists are really after. I want to put a bromine on this alkene, and I want it to go to this carbon and not that carbon. You know, so that's really the thing that's going on here. And chemists are trying to make things like medicines or agricultural compounds or research compounds. So what I said earlier about why go so far as to learn stuff like this, and I think I said to be able to predict something that you haven't seen before. So let's just see if we can take this knowledge to the next level by analogy and say, what do we think is going to happen when we react HBr not with an alkene, but with an alkyne? We haven't talked much about alkynes. I'll throw in a little bit of nomenclature just as we go along, because I didn't really do much of that either. This has 3 carbons, and so it's a propine. You have the "ine" ending. 3 carbons is prop, right? And really there's no other propines, because if you move the triple bond over here, it's still just propine, But I guess it'd be a little redundant. You could say 1 propine and number these 1, 2, 3. Okay, so back to the original question. I feel like what we've covered above allows us to predict this, even though we haven't seen this before. So think about that. If we're just memorizing reactions, we're just memorizing them, we're going to look at this and say, I have never seen this before. I've seen it when there's an alkene, but I've never seen it with an alkyne, and so I have no idea what's going to happen. But if you go back and understand like what is going on here, I think hopefully those of you present could probably predict what's going to happen. Anyone want to take a stab, interrupt me and take a stab at it? So what is going on likely here is that this is still the same as it was before, polarized hydrogen. And so a pair of electrons from the alkyne, why wouldn't it be able to do the same thing as an alkene? And it can. So it's going to form a bond. One of these 3 bonds is going to break. You're going to form a bond to hydrogen from one of these carbons and kick off the bromine, since hydrogen can only form 1 bond at a time. And there's one more thing we learned above. If Markovnikov's rule applies, if the more stable carbocation is going to form, then we have to form the bond to hydrogen to the carbon that already has more hydrogens, which is the one on the left, carbon 1. So we add a hydrogen to carbon 1. We now are left with a double bond instead of triple bond, right? And then this methyl group is still there, and the plus charge is on the carbon that had fewer hydrogens to start with. So I'm really just applying what we learned above to this, and the only difference is instead of a double bond to a single bond, you're going triple bond to double bond. The bromine that was kicked off now can come back and form, be consistent here, form a new bond. Forms. Bond breaks over here. And so the result of that one last arrow is, and I'm just going to redraw this the way an alkene really looks, trigonal planar. And so without having ever seen this reaction before, if we understood what was just above here, we were able to predict what was going to happen here. That's a really huge deal in organic chemistry. To recognize a pattern and a setup like this, that this is going to occur the same way. Any questions on that? So this molecule here at the end has no cis or trans, right? You have to have two different things attached to each carbon basically to have cis and trans. So like if I was to switch the hydrogen here and the methyl here, it's still the same molecule because these two over here are the same, and you could just flip. So these are the same. Basically, you can pancake flip this, right, and go back and forth from top to bottom. So no cis trans here. But I went looking for it. I went looking for it because like above, well, that's a different situation. So in other words, if you react an alkyne in this way, you may get cis and trans alkenes. And it's easy to see how you can get to that if I just use a different alkyne in the beginning. Oops. Let's go HCl this time. Doink, doink. It's always the same. CH3. H. In this case, there's no preference because both carbons neither carbon has a hydrogen on them. And then you get the plus, CH3. And then from here, you could go to either one. So you could get CH3C, H, Cl, sorry, Cl, CH3. So you've added HCl and, not or, CH3, C, CH3, Cl, H, added C, HCl, trans, cis. Regarding, so the two methyls are trans to each other. The chlorine and the hydrogen are trans. Here, the two methyls are cis. The chlorine and the hydrogens are cis. You have to do a little more explaining when there's more than one pair of things that can be cis and trans. There's actually another way to describe that, but we won't go into that. Okay, so another way to look at what I've been doing is that I keep asking questions. What if, so we go from, first we have an alkene reacting and, all right, here's how it goes. What if both carbons have different things attached? That brought us to here. It's like, oh, when they have different things attached, there's a new trend described by Markovnikov's rule. Then I say, well, what if it was an alkyne instead of an alkene? It's like, oh, well, I think I know enough to predict how that's going to go. It's going to go like this. It's going to leave an alkene product in the end. And then I say, what if the alkene was like this? Would that lead to cis and trans? Yes, it would. So this is classic science thinking. You know, we keep saying we're not satisfied. We're never satisfied. There's always another question to answer. Everything you learn in science brings up new questions. It's like, it's funny because it feels satisfying at the moment when you figure something out, and then very soon after that you realize, oh, maybe I should try this, which is exactly what's going on in my research lab right now with a particular reaction I've been working on. It was a base reaction. It kept giving me the wrong product, and then I said, well, what if I try this? And then it still gave me the wrong product, and then I said, well, what if I tried this? And I keep thinking of new things to try. I mean, eventually I think I'll run out of things to try, but anyway. So that little rant brought us to just nearly the end. I want to make a couple of more. The next topic is, next up is aromaticity. And I'll probably cover that in the next video. So I'm trying to keep like the videos and the in-person sort of in sequence. But we're going to still have another in-person before the next quiz, which is a week from tomorrow. So next in-person is next week. And we can use that, maybe use that time for problem solving. Problem solving, practice, maybe even some review. So those of you who are here, which thank you very much for being here. Problem solving, practice. You know, maybe next time, if you have problems you'd like to see solved, we'll have time, I think, next time. And then next Friday, the quiz will be due. I mean, the quiz will be, you know, sent out and do the same 24-hour period. Next quiz from tomorrow. And so the aromaticity stuff, that's in chapter 13. The reading and practice problems have already been assigned. I actually have a few more things to loose ends to tie up on nomenclature of alkynes as well. So we'll just touch on that in the very beginning, but mainly this stuff. So we're just out of time. Anyone have any final questions or comments? Or if you want to stick around and speak to me one-on-one, that's another possibility right now. Okay, I'm not hearing anything, so I'm going to end the meeting now and talk to you anytime. I'm available for Zoom appointments as well.
Thank you.
Thank you.
Thank you.
Yeah, don't hesitate to contact me. Okay, have a good rest of the day. Nice weather's here.